Okay, this is sections 1.3, and we're going to continue our discussion for limits. In section 1.2, we evaluate limits looking at the graphs, so graphically or numerically, a table of values generated by yourself, or looking at the table on the calculator. However, we don't always have to do this. Sometimes we don't want to take the time to graph it or make a table of values or look at the table of values for on the calculator. So we're going to look at it analytically. Instead of always having to graph it, let's kind of examine some facts and then find it algebraically or find it by another method. So nicely, sometimes when we evaluate our limits, our functions, the function is going to be defined at that location, and you won't have a whole or a special case. So the value of the limit is just going to be when you plug that number in and you find the value of the function at that number. So sometimes you can plug in C to determine the value of the function. This is called direct substitution. So here are your basic rules when you use direct substitution. If it's a constant function, then as x approaches c, the value of the limit is just going to be b. And you can just, if it's defined at that location, then plug c into x and the value of the limit is c. Same here. All right, so look at these three quick examples. This is a constant function. As x approaches 2, the limit of that constant function is going to be 3. X is defined everywhere. It's just a linear graph, so the value of this function as x approaches -4 is going to be -4. When I substitute I can take direct substitution, put 2 in for x, and I get 2 squared, which is equal to 4. So turn in your book to page 59, and here are some properties of functions, of limits. And the most important one that we're going to be covering really would be number 1, and I'm going to mention that when we use it. But basically, number 1 means if I want to evaluate the limit of a function and it's got a coefficient in front of it, I can pull that coefficient out front of the limit and then evaluate the function at that location. So we're going to be practicing these particular conditions. Look on page 60, example 2. And it says the limit of 4x squared plus 3 as x approaches 2. Now, it's using these properties just to so you can see them in action. You don't have to split it up. You can go ahead, since this is defined everywhere, it doesn't have a hole. Let's just do direct substitution, put 2 in there. 2 squared is 4. 16 plus 3 gives you 19. So, again, we use that direct substitution. Now then, polynomial functions are basically what you're going to be evaluating the limits of. They're the ones that occur most often that we're going to be studying. Again, we're looking at what happens at one location on a graph. That's why the graphs and the numerical work is so important, and talking about the graph at the same time. So this is talking about a polynomial function. You can just use direct substitution. Just plug in the value. And if you have one that's a rational function, meaning a fraction of polynomials, to find the value of that limit, if direct substitution works, you can just plug it into the numerator and the denominator and get those values. All right. So let's look at this next example. Evaluate x squared plus x plus 2 over x plus 1. This is a rational function. It's in polynomial in the numerator and polynomial in the denominator. Notice that it does exist at 1. We're not limited, so we can use direct substitution. So let's go ahead and plug in 1. So that gives me 4 over 2, which is 2. But what about if I was trying to find the limit at x equals -1? Could I find that limit at that location? Let's talk about that tomorrow in class. So we're going to expand the types of functions that we're going to be finding the limits of. So that means either we can look at the graph, or we can look at the table, or we can examine it analytically. And the first method we've used analytically is direct substitution. So far, we looked at a polynomial function. That was example 1. We've looked at a rational function. We're going to look at composite functions, function within another. We're going to look at functions with radicals, trig functions, functions that agree except for one point, a whole. And we're going to do a couple more limits of trig functions, and we're going to look at what happens when we have to do a little bit of tricks with our functions and simplifying. These are all the properties for when you're evaluating the limit of a trig function. But here it summarizes how to find the limit of a function. We have all different types. So you first go ahead and try that direct substitution. If that doesn't work, if it's somewhere that is undefined, let's use a little bit of algebra, which is what we're going to be using next. If none of those work, then we're going to have to graph it or use a table of values. So let's look at finding limits algebraically. Remember, we've used graphically, numerically, and direct substitution. Let's do a little bit of algebra. Sometimes when you use direct substitution, it produces a form that cannot be evaluated. This is called the indeterminate form. If you receive a 0 over 0, that is known as the indeterminate form, or a 0 in the denominator. So therefore, when we get this indeterminate form, we can't use direct substitution. We have to find another method. Example 6. This one should look kind of familiar to you. We discussed it that first lesson. We plug 1 in the numerator, you get 0. And plug 1 in the denominator, you get 0. 0 over 0 is the indeterminate form, so we can't use direct substitution. We have to find another way to find the limit. So we already know graphically how to find that limit. Let's use a little bit of algebra. Recall from pre-calculus and from algebra 2 how to factor a difference of two cubes. So x minus 1, x squared plus x plus 1 over x minus 1. So I'm just taking out common factors. I'm going to simplify the expression. The x minus 1's drop out. Gives me x squared plus x plus 1. Now I have a polynomial function that I can easily do direct substitution. It's not undefined somewhere. I can find the value. I'm going to plug 1 in, and I get 3, which confirms what we found on the first day from section 1.2. Okay. The dividing out technique. Okay, so again, if I plug in negative 3 makes the denominator equal to 0. I can't use the direct substitution. It gives me the indeterminate form. So let's see if we can factor this expression. So I want x plus 3 to be a factor, because if it is, these two can drop out. Lucky for us, x plus 3 is the factor of the numerator. These two drop out. The limit as x approaches negative 3 of x minus 2. Now x minus 2 is nicely defined everywhere. It doesn't have a hole. I can go ahead and plug in through direct substitution negative 3. Negative 3 minus 2 is negative 5. So again, we're looking what happens. We look at one location using another method. All right. Sometimes our functions look kind of scary and they're not going to behave. Notice that if we plug 0 in for x here, you're going to get, through direct substitution, 0 over 0, which is the indeterminate form. But it doesn't factor like the previous expression. So, now, remember, notice I've been writing limit each time. I'm not just doing my algebra independently. Once you are evaluating a limit, all algebraic manipulations have to remain in the limit form. Develop good habits right here. Keep writing your limit each time. Don't drop it just because you're doing algebra. It is still a limit. We're just changing the form as we go along. I'm going to multiply by something to change the form of this fraction. Recall that if I want 1/2 to have a denominator of 6, I have to multiply it by something to make a denominator of 6. That in-between step is I multiply it by 3 over 3, which would give me 3 over 6. You know 3 over 6 simplifies to 1/2. 3 over 3 is really just a form of 1. But I can multiply by 1 to change the form of 1/2 to make another fraction. I'm going to use the same process here. I'm going to multiply by 1 but I'm going to change the form of this fraction so I can use direct substitution. You're going to multiply by the conjugate of the numerator. All right, so the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Conjugate of the numerator means everything stays the same but the sign in the middle. This is plus 1. Remember, I'm multiplying by 1, so everything stays the same on top and bottom. And I'm just changing the form of the fraction, so it's still a limit question. Now, remember when you multiply the same terms times each other, but the middle signs are different, it's just a difference of 2 squares. So I'm not going to FOIL this. I'm going to depend on you to remember algebraically how to simplify this. This is x plus 1 minus 1, and I am not going to multiply the denominator. There's no need to. So the 1's drop out. I have x over x, square root of x plus 1. Plus 1. Again, these drop out. And now I'm left with 1 over square root of x plus 1 plus 1. At this point, I can now employ direct substitution because my denominator can be defined. It won't drop out. It will drop out if I had a not minus sign here. I have a plus sign now, so everything works out. So putting in 0, 1 over square root of 1 plus 1 is 1/2. Now then, let's look at some properties with some trig functions before we do these two. And I'm going to go to the last page of your notes. And notice that you've got 2 trig rules here. One says sine x over x, and one says the limit as x goes to 0, sine x over x is going to be 1. And we'll talk about in class why this is true. We're just going to use it tonight for our notes. And if you ever have this form, the limit as x approaches 0, 1 minus cosine of x, that's equal to 0. And we'll talk about that also tomorrow in class. So if I'm just evaluating the limit as that sine x over x, that's just going to be equal to 1. So what allows me to use this rule is the coefficient of x and the coefficient of x in the denominator are the same value. But this guy does not follow the rules. He has a 4 sitting there. He needs a 4 in the denominator. Again, I'm going to use algebra to help me make this look correctly so I can use my rule. All right. So for me to use this rule, I need a 4 in front of my x. So if I multiply by 4 over 4, and I use the commutative property for multiplication, I can rearrange some things. I'm going to pull this 4 in front of the sign. I'm going to put this 4 next to x. Again, I'm just using commutative property multiplication. So 4 times sine 4x over 4x. Now I'm going to use the properties of limits. I'm going to pull this 4 in front of the limit notation because he's just a constant. The constant can go in front. All right, so since this whole thing now is in the correct form, this is 4 times using substitution property, 1, the limit is equal to 4. Now let's go back to this particular example. The limit is x approaches 0, tan x over x. Well, we don't have a rule for that, so let's change tan x to sine x over cosine x all over x. And it still doesn't look like a rule I can use, but I can separate the sine x and cosine x. And I'm going to take that a step further and write this as limit as x approaches 0 of sine x over x times 1 over cosine x. All right, I know what happens here. Now remember your properties, I can evaluate each of these separately. So I've got the limit as x approaches 0 of sine x over x times the limit as x approaches 0, 1 over cosine x. This from the rule is equal to 1. Let's do direct substitution. Cosine of 0 is 1. 1 over 1 is 1, so the answer is 1. All right. Your homework is listed on your assignment calendar. We just finished section 1.3, and we'll discuss these limits tomorrow in class, plus add a couple of things from our notes.